In this class, we will discuss finite difference method for numerical differentiation. So, unlike in the previous example for numerical differentiation, here we will be having a function. That function has to be differentiated numerically. Okay, so here we don't have to do any interpolation technique. We can directly differentiate the given function numerically. Okay, so here this finite difference in this finite difference method, we have the forward method as well as backward method and central difference method. All are there. Okay, so the three different classes are there that we will discuss in this section. All those equations corresponding to those backward, forward, as well as central difference method we will discuss. Okay. So first we consider here the first derivative at point x, okay, by using this finite difference method, and which is defined by using this limit as f dash of x equal to df by dx, which is equal to limit delta x tends to 0 delta f by delta x. Okay, so this is the definition of any derivative of this function f of x through this limit. Okay, so if you consider any function and if you want to find out uh, what is the differentiation of that function at any point x, then that can be defined by using limit as this equation. Okay, so when delta x tends to 0, the change in x value tends to 0, delta f, change in f divided by that delta x, that will give you the corresponding differentiation at the point x. Okay, so that is the definition of differentiation numerically for any given function f of x at a given point x. Now, as you know, this delta x, value of this delta x, that cannot be infinitesimal, and so that it should have some certain value. Okay, so it is not that much infinitesimal when you are considering it numerically. So in numerical differentiation, what we get is an approximated result. We will not get the actual result, but we will get an approximate result, and that depends on this delta x value. This delta x value, how we are choosing that delta x value. Okay, so in graphically we can represent this particular thing. We can represent this graphically. Let us consider this y. Consider this y axis as your f of x. This is f of x, and this is x variation in x axis. And if you consider any function, let us consider a function like an exponential decay or something. Consider any function, and if you want to find out the dy by dx at, for example, this point, then at this x. Okay, so we want to find out dy by dx at this point. So basically, if you consider a tangent at this point, consider a tangent at this point. Consider like this. Tangent passing through this point. It is right again. Any curve you can consider. So let me do more. Something like this. And if you want to find out the dy by dx at that particular point, then you can consider tangent like this, which is passing through that. Let's say this is point A. Okay. Now consider another point somewhere here, which is the point B. And if you draw that tangent for that particular point, then it will be like this. So this drawing may not be that much good, but so you can see these two tangents make a large angle. You can see that these two tangents will make large angle between them. So when you are having this delta x variation, if you are considering this as your first point, this is your second point. So delta x is this difference. If delta x is much larger, then the points are, which means that the points are well separated. Okay, so in that case, these tangents are very much different. So that your solution, when you do the differentiation, your solution will also will be very much different from the original solution. Okay, so when you make this b close to a, very close to a, so that the delta x is very small, approaching to 0. In that case, if you calculate what is your change in f with respect to that change in x, okay, then you can get this function, this differentiation at that particular point, almost which is approximately equal to the original solution. Okay, so that is the basic principle of this method. And when you consider that, so basically we have to reduce this delta x value as much small as possible, so that we get an accurate result. If it is larger, then we will not get an accurate result, because this, you can see this, the slope is very different. The value of differentiation will be different if you consider this delta x very large, because if you consider these 2 points A and B, you can see the tangents that we draw, that is very different from if you compare that two tangents. But when the point B is, suppose it is very close to A, then the tangents will be almost similar. In such case, you can consider the slope at that point, at that point, if you consider the df by dx in such a way that the x is approaching 0, very small. And if you consider what is the change in function f of x at A and B, that is the change f of A and f of B, that is the change f of A minus f of B. So that is the change. With that change in x, if you consider, then that will give the almost approximated solution for the given function. So solution means differentiation of that particular function at that point. Okay, so when delta x is small, you will get much more accurate result. So in this case, we will get this f dash x for the approximated value. This f dash x, you can write it as f dash x is approximately equal to f of x plus delta x, that is the b point, minus f of x divided by delta x, that is the change in function f, that is this term, numerical term, a with the change of x. Okay, so that you have to find out when x is these 2 points are very close to each other. Okay, that is the differentiation that we have to do numerically. So f dash x will be the function differentiation of f of x at x, that will be given by f of x plus delta x minus f of x by delta x. So that is the equation for the first derivative of that particular function, and where you can also replace this equation by x plus delta x equal to xi plus 1, x with xi, and delta x with h. And h, you can see this is a conventional method that we use. Okay, so that is the separation between those 2 points, or change in, this is nothing but change in x. So this one is f dash x. So then we can replace this one, equation number 1, like this: f of xi plus 1 minus f of xi all divided by h. That is the differentiation, first order differentiation. Similarly, you can look for second order differentiation, f double dash of xi, that will be equal to f of xi plus 2, I plus 2 minus 2 times f of I plus 1, f of xi plus 1 plus f of xi divided by h square. So this one will be f of, in this case it is delta, if you consider delta x equal to h, so this will become, what is this? F of x plus h, because delta x is h, minus f of x, right, divided by h. Similarly, here we will be having x of f of xi plus 2. So in that case, it is, we can write f of x plus 2h minus f of, sorry, 2 times f of x plus h plus f of x divided by h square. So this is the equation for second order differentiation of that particular function f of x at xi. Okay, in this case it is at xi. We are considering x equal to xi here. So at any given point, you can find out the numerical differentiation of that given function by using these two equations. This is for the first order derivative, and this is for the second order derivative of this function. Now we'll go to the mathematical part, or the derivation of this equation, how we can get these equations. So in mathematical part, first let us consider the forward finite difference method. So in forward finite difference method, first you consider the Taylor series expansion of f of x, any function f of x. You can write it as f of a plus f dash of a by 1 factorial into x minus a plus f double dash of a by 2 factorial into x minus a square, also plus etc. So this is the Taylor series expansion of any given function. We can write, for example, let us consider x equal to xi plus 1 and a equal to xi, and x minus a. So that is the difference. If you consider a equal to xi, which means that the point where you had to find out the dy by dx, df by dx. So let us consider that point as a, that is equal to xi, and x minus a, that is the x is xi plus 1. So xi plus 1 minus xi, that is the term, and that is directly h, this difference between the adjacent x values, and that is nothing but delta x, change in x, that we already discussed. Okay, so in that, if you substitute all these values in this equation, in this Taylor series expansion, then we will get f of xi plus 1. We are considering x equal to xi plus 1, so this is f of xi plus 1 equal to f of xi, a equal to xi, and plus f dash of xi into h plus f double dash of xi by 2 factorial h square, because x minus a here is h, plus f triple dash of xi by 3 factorial h cube plus etc. So this is the Taylor series expansion. And now if you consider this Taylor series expansion and take this f dash of xi alone, so f dash of xi, I can write it as f of xi plus 1 minus f of xi, take this to the other side, okay, divided by h. This h will, you take this h also to the other side, keeping this f dash xi on this side. So ignore this part, higher order part. If you ignore, then we can write, I will just do that here. So if you ignore these higher order terms, h square, h cube, all those terms, because h is very small, so that you can neglect these h square, h cube terms. When h is very small, h square will be very, very small. H cube will be much smaller than this h square. So these terms will be very small. so that we can neglect that. Then in that case, we can write this f of xi plus 1, which is equal to f of xi plus f dash of xi into h. Okay, so this is the equation, neglecting the arrow terms. So we'll get f dash of xi. So I'm keeping this one, and that will be equal to f of xi plus 1 minus f of xi. This you take to the other side, divided by this h will come. So this is the equation for first order differentiation of that function numerically. And you can have some plus some error term here. Okay, some error term in the order of h. So this is coming from this higher order term. If you are neglecting that, okay, then some error may come here. So this is the equation for first order differentiation, and in that differentiation you will be having some error because you have neglected this higher order term. Some small value that may come, but you have neglected that, so that can be considered as estimated error here. Okay, that you can see. So that is in the order of h, order of h. That's why we are getting some error of h, which is in the order of h. Now, if we consider the backward finite difference method, what is this backward and forward difference? That we'll just tell. We'll just explain that here. So backward finite difference method, in this case, we'll consider x equal to xi minus 1 and a equal to xi, and x minus a equal to xi minus 1 minus xi. In the forward difference method, this was xi plus 1. Here it is xi minus 1 minus xi. So we are considering the x value which is lower. Okay, so which means that your xi minus 1, this value will be smaller than, which is less than xi. Okay, so in that way we have to deal with when you are considering the backward finite difference method. So xi minus 1, which is smaller as compared to xi. In the forward difference method, we are considering xi plus 1, and that one is greater than x of I. So that is the difference. And if you consider f of xi minus 1 here in the Taylor series expansion, the difference comes in this sign. You can see here it is a negative sign. Again, it is a negative sign here. So we don't have any continuous positive values, but instead of that, we are having negative signs here. So in the first term, we have positive. This one is positive term. Second negative, then again we are having positive term. So we can see the h value with even power, okay, like h raised to 0, h raised to squared, h raised to 4, all those values will be positive. All those terms will be positive. But this h with odd power, those terms will be negative. H with odd powers will be negative. Okay. In other words, you can also consider it like this. If you consider f dash x, then also you can get that negative and positive part. In that way, also you can define that. Or simply by using h, you can define if it is having even powered h term, then it is positive. If it is odd powered h term, then it is negative. That term will be negative. So that is, there is an alternation of these signs for each terms in the case of backward finite difference method. So if you continue the same process that we did for forward finite difference method, then we'll get this expression. And remember, here it is f of xi, which means that f of x minus f of x I minus 1. So this is f of x minus h. We are considering x I minus 1. So this is f of x minus h divided by h. So this is the expression for f dash of x. If you consider for x, this is the expression. If it is xi, then you have to consider xi here also. Okay. So this is the expression when you are considering the numerical differentiation by using this finite difference method. When you are considering it is backward, okay, backward finite difference method. In forward, it is f of x I plus h minus f of x. In backward, it is f of xi minus f of xi minus h. Okay. So that is the difference. And if you consider the central difference method is nothing but subtracting the backward Taylor series expansion from the forward Taylor series expansion. Okay, then you will get the differentiation equation like this: f dash of xi will be equal to f of xi plus 1, which means that f of xi plus 1. So that is f of x plus h minus f of xi minus 1. So this is f of x minus h divided by 2h. So this is the expression for f dash of x when you consider central difference method, and some error terms also there. In this time, this error term is in the order of h square. Okay, so the error will be much smaller. Why the error is, why you can see this is h square. So if you consider the previous cases for forward method and backward method, we are having error of the order of h, which means that if you consider h is equal to 0.1, something like that, then your order of error will be in this fashion: 0.1 in point first decimal places. You can see this in this range. So this will be having this much of error. But if you consider central difference method, your order will be h squared. Error order of your this h value for the error term, that will be h square for error. This is the order. So this is nothing but 0.01 if you consider h equal to 0.1. So your error will be much smaller when you consider central difference method. And that you can also get from the graph also. So if you consider this as your point A and this is your point B, okay, and this is the difference. This is the difference in x, delta x, or which is equal to h. So if h is small, you will be closing to this A. Okay. Otherwise, you are getting a different value. So you'll be having different slopes and you will be getting the, different value from the original solution. But when you are doing the central difference method, you are actually calculating the point at here. Okay. When you're considering the central difference method, you will be calculating this at this x. So this is x plus, sorry, this is x minus h and this is x plus h, and in between these two you are having this x value and are calculating at this in between these two. So you'll be getting a much more close result when you're considering the point, this point. Okay, so that's why it is having less error as compared to the other forward and backward difference method, and that is basically you can get from here also. This is in the order of h square. So the error will be less when you are using the central difference method. Now let us do one example, then you will be able to understand that more clearly. So first we will consider this example. Find first and second derivative of the given polynomial. So that is at x equal to 0.1. So we have to find out the first order and second order differentiation of this polynomial at point x equal to 0.1 numerically. Okay, this is numerically. So how we can do that? Also, we have to compare what will happen for h equal to 0.1, 0.01, and 0.0001. What will happen when you reduce that h, which means that basically you are reducing delta x, change in x you are reducing. So what will happen to that cases, all those cases, what is the observation? So first you have to calculate f dash of x. F dash of x will be df by dx, which is equal to, as you know, you just differentiate this polynomial with respect to x, so that this 4 will come here, 4 times 0.2 times x cube. So that's what is first term. And then you have to differentiate the second term, 0.5 x cube. So this 3 will come here and 3 times 0.5 times x square will come. So that is the second term. Then this term, if you differentiate, that will give you 0.3, and this term will become 0. Okay, and so that we'll get equation like this for the differentiation, that is f dash of x, and f dash of 0.1 we had to find out. F dash of 0.1 at x equal to 0.1, we had to find out what is the value of this f dash, that is the function derivative. So if you substitute 0.1 for x in this equation, then you will get 0.2858 as your answer. That is analytically. Okay, so we are just doing this differentiation analytically and substituting x value. And similarly, if you calculate what is f double dash of x, you will get this equation. You just have this 3 multiplied with this constants 0.2 into 4 times x square will come, and this 2 you have to multiply these coefficients. 2 times 3 times 0.5 into x, this term will become 0 when you differentiate that. So you'll get this kind of equation for second derivative of that function, and f double dash of 0.1, if you calculate, substitute x equal to 0.1 in this equation, and you will get this kind of expression, and that will be minus 0.276 for the second order differentiation of that function at x equal to 0.1. Okay, now how we will do that numerically? So this whatever we have discussed is for analytical solution. So now let us consider how we can do it numerically. Okay, so in numerical method, as we discussed, we are having this equation f dash of x equal to f of x plus h minus f of x by h. So this is the forward difference method. I'm just explaining only the forward difference method. You can do it by backward difference and the central difference method also. You can try that. So by forward difference method, we are having f of x plus h minus f of x by h. And if you are considering backward, it is f of x minus h minus f of x by h. Okay, so that you have to keep it in mind. So f of x plus h means what is x value? X we have to find out, that is 0.1 value of x that we have to find out, the point where we have to find out the dy by df by dx. So that is 0.1, x equal to 0.1, and h, let us consider for h equal to 0.1 what will be the value. We are considering only one step, that is the subtraction between the x values 0.1. So now if you consider this delta, which means that the delta x h equal to 0.1 means delta x equal to 0.1, x equal to 0.1. So we are considering 2 points in that function, in that curve, which is having a suppression of 0.1. Okay, so that is that's why h is equal to 0.1. So that what will be the result? So f of x plus h, what is that? 0.1 plus 0.1. That will be f of 0.2. So this is nothing but f of 0.2. And f of 0.2 will be, just substitute 0.2 in that f of x equation. So that will give you this particular solution minus 0.44368. Similarly, find out what is f of x. So f of x, what is x? X is, we had to find out the value of function at x equal to 0.1. So substitute that 0.1 here and substitute that 0.1 in the function, given function polynomial. Then we will get minus 0.47048 as your answer. And now subtract f of 0.2 minus f of 0.1. Why? Because f of x plus h minus f of x we have to do, and divide it by h. So if you do that, you will get 0.268 as your first order differentiation value at x equal to 0.1. Okay. So I'm not going to do second order differentiation. You can do it by yourself and check uh, uh, the values. Okay. So this is how we can do that by numerically. So numerically, you can see this is 0.268 for h equal to here we have used 0.1, h is equal to 0.1, which is a larger value. Anyway, so that is the 0.268 is the numerical value. Okay, what was the analytical value? Analytically, how much the f dash x analytically, we just find out what is f dash x equal f dash of 0.1 analytically, that is equal to 0.2858. That is what we did earlier. So this is the analytical result. So you can compare these two numerical and analytical results. You can see some difference after this. So 0.268, here it is 0.2858. So there are some small variation, and let us see what will happen when you are reducing this h to 0.01 and 0.000. Okay, so for that we'll discuss the program corresponding to it, so that we can see the change. So first I will show you the okay, let me see whether it is okay. So I will just go to this window for doing the program. So I will just copy the program here and see. Okay, so okay, I will share that screen. So I will just change the screen now. Okay, I hope you can see the screen. Yeah. Okay. So you can see the program corresponding to this finite difference method. Here I have shown only the forward difference method. So you can see here it is first I have imported numpy as np, and then import math. This one is not required. Anyway, so import numpy as np. Okay, if you are using any of that functions. So again, we are having define f of x, where you have to define your function, that is 0.2 times x raised to 4 minus 0.5 times x cube. So that is your polynomial in the given problem. Okay, so first I have to define that particular function, and here I have given this one is for the f dash of x. Okay, that is analytically. So this is just analytically. This is not required for this program, but just to compare. Okay, just to compare, I have used this particular function. This is just a differentiation of this function f of x analytically. So that we have already done theoretically in paper. I have shown that. So that equation will be like this. Just to differentiate this analytically, and then you will get f1 of x. Now you just consider x equal to 0.1, where you had to find out the derivative of this given function, and consider h value, which is equal to 0.1, which is also 0.1, and the first order differentiation, that is FOD, that is given by this. That will be, so this FOD will give you the numerical differentiation, numerical first order differentiation value of that particular polynomial, which is defined here. Okay, at x equal to 0.1. That's what we have to calculate. And second order differentiation also I have defined here f of x plus 2h minus f of x, minus 2 times f of x plus h plus f of x all divided by h square. So that is for second order differentiation for the case of forward difference method. Now what I have to calculate? I have to calculate this FOD, that is first order differentiation at x equal to 0.1, and SOD at second order differentiation at x equal to 0.1. So automatically it will take x equal to 0.1, that is that I have already defined here, given here value of x, and h also I have given 0.1. So it will just calculate these two by using these two values. At the same time, I am also printing the analytical solution by using this f1 of x. So by using this, I think I have. So you can see this f1 of x is nothing but differentiation of this analytically. So I will just calculate what is this value of this function at x equal to 0.1. So that will give me analytical solution of the differentiation at x equal to 0.1. Okay, so I'm calculating f1 of 0.1 here. f1 of 0.1 is nothing but when you are substituting x equal to 0.1 in this equation, what is the value? That's what we are calculating. That is corresponding to the differentiation, first order differentiation analytical. Okay, so I will just run this code. I hope you understood this, and I am printing here numerically the first order differentiation is FOD, that is the first order differentiation value, that is calculated by using this equation f of x plus h minus f of x divided by h. And for second order differentiation, numerically, second order differentiation is, so that you can change this textures you can change. You can include a second order differentiation at x equal to 0.1 and all those things that you can include. That is no problem. You can format that. There are different types of printing methods available. So just run this. I will just run this program, and you can see these are the values. Let me see, that is, oh, this is just the function. So this is not required. So this is also not required. That I have used for some calculation. Okay, now you can see, you can also use that f of 0.2 and f of 0.1 that you can use to verify the result that you got theoretically. So in this program, you can see analytical solution is 0.2858 that we have got. Okay, we have already calculated that value, and then numerically if you calculate, then it is giving me 0.2857. So what was the value we got for numerical calculation? It is for numerical calculation, it is 0.268. Right, this is, I think it is okay, this is 0.001. Let me change this 0.1 and run it again. For h equal to 0.1, it was different. Okay, now you can see this is 0.268. That is what we have got theoretically. Also we did these calculations, and the numerically we got second order differentiation, which is equal to minus 0.5. Okay. So you know, original solution or analytical solution is 0.2858. Okay, and numerical solution through this program that I got 0.268, and that is the same as what we get when we do that theoretically. So there are some difference. So the program is okay because we are getting same result as we did theoretically, and now there is a difference from analytical solution as compared to numerical solution, and that is because of this h value. When you reduce this h value, which means that if you are reducing that delta x, change in x between those points and b, so if you reduce that, let's say 0.01, okay, and now you can see this is now I will run. First you see this is 0.268 and this is 285, and now I will run after making it h equal to 0.01. You can see now it is 0.284 and this is 285. Now when you are reducing the h value, it is getting much closer to the analytical value. Now if you further reduce it, let's say 001, this was the question for 01 and 001, what will happen? So now you can see the solution is analytically it is same 2858, 0.2858. So here we can see 285 and 78. So it is almost okay. So when you are reducing this step, this h value, delta x value, change in that points, that will give you a very close result, almost same result as the analytical solution. Similarly, you can also see change in the second order differentiation also when you are changing h value. Okay, so because in the first time we got here 0.5, now it is 0.276. This is the second order differentiation of that particular polynomial at x equal to 0.1. So this program is just for the forward difference method. You can also do the same for backward difference method, changing x plus h to x minus h. Okay, and also for the central difference also you can try by using this. You just have to change that equations. Okay, so that's why I'm not going to do that. We just change these equations for first order and second order terms. This x plus h you have to change to x minus h and calculate for backward. And in the third case, in the central difference method, you will get f of x plus 2h minus f of x plus h plus f of x, right? So you can use those equations and calculate what is the corresponding differentiation value. And also you will get for central difference method, it will be much more accurate. The error will be very small. Okay, so that's all about the finite difference method for numerical differentiation.